see my screen. Yeah, hi everyone. Thanks for inviting me. My name is, as I said, or as William said, my name is Martin Gauch. I'm a research scientist at Google Research, and specifically, I work on the team that builds and operates the Google Flood forecasting system. And so, in this talk of like 15, 20 minutes, my goal is kind of to give you a brief overview of what Google Flood forecasting system is, if you haven't heard of it, and then give a sort of an update on what happened in the last year or year and a half in terms of increased coverage, increased accuracy, new features, and so on. Yeah, so let's get started. If you don't know Google's flood forecasting system, what this is really a global AI-based model, which started originally back in around 2017 in regions around India and Bangladesh, but by now is really a global system covering more than 100 countries and providing flood warnings and notifications for up to 700 million people. So really quite a large coverage and quite away from the beginnings in individual places in India and Bangladesh. The way that the system works is, in some sense, split up into three components. The first one is the hydrologic model. So this is really the deep learning model that predicts the stream flow in places along a river. And then this makes forecasts for up to 7 days into the future. And those forecasts we pass into a second model, which is the inundation model. And that combines these hydrologic forecasts with topology information, with satellite information, and tries to infer sort of a spatial map of which areas we think are being flooded at this point or in the future, and which areas are not being flooded. And then finally, of course, we have to make sure that our forecasts actually reach end users. And so for that, we have a number of different channels for sort of playing out our warnings. So those depend a bit on which country you're in, sort of due to the legal situations. Different countries have different warning channels. But broadly speaking, we can send actual push notifications to Android phones. We sometimes show warnings on Google Search or on Google Maps. And then finally, we have a system that we call the Flood Hub, which is sort of our global view of the state of our forecasts, and is intended for more expert users who need more than just the information of individual places and maybe need some more detail. So Flood Hub is a public website. You can access it by going to g.co/floodhub. And I'll actually just do a quick demo of it to sort of show you also how it's evolved since the last presentation that you've maybe seen of Flood Hub. So it looks like this if you access the website. And basically what you see there is you see all of the locations that we're making predictions at, and the color indicates whether we're currently forecasting a flood or not. So all of those green places are places where kind of nothing out of the ordinary is happening. Then yellow places are places where we're predicting at least a flood of at least a severity of a 2-year return period. So something that we would expect to happen only or at most every 2 years. And then the red points are places where we expect a flood of a 5-year severity. So a flood of a severity that we would expect only once every 5 years. And then you can actually zoom into all of these places, and you will see the exact pins indicating the location where our model has made its forecast. So I can zoom in into any of those, and I will see the specific location. I will see here the inundation map also. So the blue shades indicate the risk of inundation in this case, it's for the 21st of January, so it's a forecast. And then on the left, you can see the hydrologic models forecasts or hindcasts. So the hydrograph here shows our historical predictions for the last couple of days, and then our 7-day forecast indicating that actually the water has been rising quite a bit, and we expect it to rise even further, crossing the 5-year return period threshold. So quite a significant event potentially. Here you get a bit more information. You see which hydro basin that this location corresponds to. You see the size of the basin. Soon you will also be able to see the polygon of the basin. visually on the map, which is something that many expert users requested from us. So this should launch in the coming weeks. And overall, you just get more information than you used to in the past. And in addition, you have the ability to, if I zoom out here a bit again, you have the ability to show even more gauges than what you see here. So in this current view, we're kind of showing the gauges that we have been able to verify. And by verify, I mean that we had historical data available, either in the case of historical gauge measurements, or in the sense of historical satellite imagery, which allowed us to, in some sense, check that our historical forecasts were reasonably accurate. So those are the predictions that we kind of have a certain level of trust in. But you can, if you want, and if you have additional information needs, you can activate this toggle here, which shows you a much more dense spatial coverage, because it also shows places where we haven't been able to do this verification. So you have to take all of this with a grain of salt, because it means there might be more inaccurate information here. But on the flip side, you get, or on the upside, you get a much higher spatial coverage, and you can actually follow the river network all the way from upstream to downstream and see maybe how flood waves evolve over time and over like along a longer river. So we're really thinking that for expert users, despite maybe the lower quality, this might still be really useful, especially if they have other sources to compare those predictions to. And so globally, we really have a very dense coverage now. The main exceptions being countries like Russia and China, where we're just legally not able to produce these forecasts. So this is FloodHub. And in the next couple of minutes, I'll basically spend some time and explain all of the changes in the background to the model and to the data that were behind us being able to expand our coverage to all of these new places. So I think back in, I don't know, a year or a year and a half ago when Moriya made her presentation, I think we were at like 80 countries or so, maybe even less, and now we're at over 100 countries. So yeah, I'll just explain a bit on how these differences came to be. And in order to understand this, maybe the first thing to understand is how exactly this hydrologic model works. I said before that the hydrologic model is a deep learning model. Specifically, it's a long short-term memory or LSTM network. And it gets various sources of input information. The first one being what we call catchment characteristics. So these are things like the elevation, maybe the land cover, and so on. And so that tells the model which place in the world we currently wanted to make its prediction for. And then in addition to that, of course, it also needs the weather information, which we provide partly as weather forecasts, giving us information about what we think will happen in the next couple of days, but also in terms of precipitation estimates of the that give us hindcast and nowcast information. So no forecast, but information all the way up until today. And we have various different providers for all of these weather forecasts and weather and precipitation estimates. And given all of that data, the last thing we need in addition to that is gauge measurements. So we need streamflow measurements from ideally all over the world. The more the better. And given all of that data, we can train our model, and we train one model globally. So what that means is, unlike traditional hydrologic modeling, we do not have individual models for individual places, but rather we have one model that's applied globally. And this is really key because what that allows us to do is it allows us to apply that model to places where we haven't had historical measurements, which is really one of the key breakthroughs that we had with using AI models for hydrologic modeling. And so what you see on this plot is the evolution of our training data, where you see all of the blue dots are the places that we had in the last major launch in 2023. And then we have added a lot of additional gauges from various sources, but most notably, one of those sources is the Caravan project. So if you haven't heard of Caravan before, what Caravan is really this community-driven data collection project where anyone who has streamflow information for any place on Earth on their laptop or on their hard drive, they can contribute it to the Caravan project and make it available and accessible for researchers and practitioners to use it in kind of a standard data format. It automatically generates weather forcings that go with it. So it's a very, very nice way of contributing your data in such a way that it really becomes useful for more and more people. So if you have any streamflow data available for regions that maybe are not yet covered by Caravan, I'd really highly encourage you to take a look at this project and maybe to contribute some of your data. So this is kind of the first of a couple of improvements that we did in the last year, is really adding more stream gauge data. The second major improvement that we did is we added more weather products to the inputs of our model. So previously in the last launch, we were already using EOTEC land, we were using CPC, IMERC, and HRES, but now we've additionally included GraphCast. And GraphCast is Google's new AI-based weather forecasting model, which has a very high quality and really allowed us to improve our predictions, especially in the long lead times. And the reason that we got this improvement in the long lead times is really that this is only the second forecast product that we're adding as inputs to our model. We already knew that the model really benefits from having multiple sources of weather information because it can learn about the individual errors of each of these products and kind of create a blended weather product in order to make its prediction. And now we're also gaining this this benefit in the forecast dimension because we now have multiple sources of forecasts. So the model is really able to learn in which cases is HRES better, in which cases is GraphCast better, and dynamically adjust its focus to look at one or the other or both. So adding GraphCast was quite a big improvement. However, this kind of creates this problem where we now have a dependency on 5 or 4 different weather forcing providers. So what that means is in order to create a prediction, a new flood prediction, hydrologic model prediction, we need to have all of these weather forcings available. And when you run at a global scale every day, multiple times, there will inevitably be an outage of any one of those providers sometimes. And so that created this challenge where whenever one of those providers would have an outage, we would not be able to update our flood forecasts, which is really problematic. So what we did is we created this new model architecture, which is still an LSTM-based architecture, but it's now able to cope with situations where for any point in time, any of these providers may be missing. So for example, if IMERC at any time step is not available, the model is still able to run, drawing from the information of all the other existing data providers, and still produce a flood forecast or a streamflow forecast. I'm not going to go too much into detail in this architecture. I'm happy to answer any questions about this. But kind of the key that we did here was really changing the architecture in such a way that it allows to run the model operationally in real time under the constraint of missing providers. And yes, we're using IMERC early because that's the one that's available at the time that we need it. So the question then is, of course, how well does all of this work? And in order to gauge the quality of our model, early in the last year, we published a paper where we collaborated with the maintainers and the operators of the EU's Global Flood Awareness System, or GLOFAS. And basically what we did there was we compared the accuracy of the GLOFAS model and the Google model. And this was before all of the changes that I just mentioned. And what we found back then was that Google's 5-day lead time predictions are roughly as accurate as GLOFAS's nowcast. So in other words, we're kind of gaining 5 days of advance notice of incoming flood events, which give us 5 days more time to warn people, which is, of course, a really useful thing. And then given all of the improvements that I mentioned before with additional training data, more weather forecasting products, and so on, we actually gained an additional 2 days roughly. So what you see in this plot is a cumulative distribution function of Nash-Sutcliffe efficiencies over all of the basins that we've evaluated here. And so Nash-Sutcliffe efficiency, or NSE values, kind of the most common metric in hydrology. If you're not familiar, larger values are better. So you want your curves to be as far to the lower right as possible. And what we see here is that the performance of our previous model at the 5-day lead time is roughly as good as our new model's 7-day lead time performance. So as I said, this means we're kind of now looking, we can look 2 days more into the future at the same level of accuracy, which again gives us more headroom to warn people ahead of time, and therefore is in an operational context really useful. So that's kind of the updates to the model. And then finally, of course, we're not doing all of this alone. We're also collaborating with various external partners. Partly we're doing this with researchers. We're writing papers together with other researchers. But also we're actually working with NGOs and government agencies and agencies like the WMO, because those agencies or those NGOs are often the people who have the kind of the on-the-ground knowledge, who know people in the places that are affected, and who can really reach the people that we might not reach because maybe the internet penetration is not as high, and sort of cases like that. So one example would, for example, be Give Directly, which is an organization that gives money to affected communities before a flood would hit, so that they have the money to prepare, as opposed to kind of the standard approach of giving the money after a natural disasters. When the stuff has already happened, then they can only use the money to repair and to recover. Whereas if you get the money beforehand, you can actually avoid the problems in the first place. Another collaboration is with WMO, which has this project of providing early flood warnings for everyone, and we're one of the partners there trying to make that happen. And then one of the things that we heard from many of these organizations is that they have their internal systems and processes and dashboards and so on. And so for them, having this Flood Hub UI is a nice thing to kind of explore. But in order to really make use of the predictions, what they needed was programmatic access. So what we've released in the last couple of months is actually an API that allows you to programmatically access our forecasts, and therefore being able to integrate this into your existing systems and make live requests of our forecasts to use them in whichever way fits your existing processes. A final thing that I'd like to mention is that recently we released 2 data sets, which are kind of historical nowcasts and reforecasts of the newest model that we have. So what we did is we just took the newest model that we have and we applied it to provide to reforecast the period from, I think it's 2016 or maybe 2012 until 2024, so that you have historical predictions of the model, which could be useful for either historical analyses or comparing to other existing models that you've maybe so far been using. So both of these resources, the API and the data set, I can just paste some links after in the chat, but you're also welcome to reach out to me. This is my email address.